Welcome to this explainer. I've spent 30 years operating ultra-pure water systems, specifically reverse osmosis and mixed bed setups. And today, we're diving into a real troubleshooting masterclass. We're going to look at a highly critical failure scenario. What happens when a mixed bed system goes totally wrong after regeneration, and exactly how we fix it.
We've got a lot to cover, so here's the game plan. First, a quick mixed bed technology overview. 2, the incident description and symptoms. 3, identifying the potential causes. 4, root cause investigation steps. 5, a detailed troubleshooting action plan. And finally, 6, summary and key takeaways.
Let's jump right into Section 1, Mixed Bed Technology Overview, the anatomy of our high-purity polishers.
What's truly fascinating about this process is the internal architecture. A mixed bed unit is essentially an intimate mixture of strong acid cation resin in the hydrogen form and strong base anion resin in the hydroxide form. During a normal service cycle, every single cation bead is sitting right next to an anion bead. So any acid produced by the cation resin, it's instantly neutralized by the neighboring anion resin. This brilliant little design is what drastically reduces sodium and silica slip, giving us that incredibly pristine water.
To put this into context, let's look at the larger plant layout. Raw water flows through multimedia filtration, hits the cartridge filters, pushes through the reverse osmosis membranes, and then finally arrives at the mixed bed. This is it, the critical final polishing step. It carries the absolute ultimate responsibility for your water quality. If the mixed bed fails, there's no safety net left to catch the mistake.
And how do we actually measure that ultimate quality? Resistivity. In heavy-duty industries like semiconductor manufacturing, hitting a water resistivity greater than 15 megaohms is absolutely non-negotiable. It's make or break for production. That 15 megaohm mark tells us we have a near-total absence of conductive ionic impurities.
Moving to Section 2, Incident Description and Symptoms, the crisis moment. Okay, picture this. You've just finished a complete regeneration cycle on your mixed bed. You're feeling good, you put the unit back online, but instead of seeing that pristine water, the quality just crashes. Your resistivity plummets below 10 megaohms, and the lab is suddenly reporting severe silica leakage. Let me tell you, this isn't just a minor blip. This is a massive, systemic failure in your regeneration process.
The real nightmare is unfolding right inside those massive industrial vessels. What happened is that during the initial backwash step of the regeneration, the cation and anion layers simply failed to separate cleanly. Because they stayed mixed together, injecting the chemical regenerants led to severe cross-contamination.
Which brings us to Section 3, identifying the potential causes, the usual suspects.
So, why didn't the resin separate? In my experience, it almost always comes down to a few core mechanical issues. Number 1, your backwash flow rate is off. It's either way too high or way too low. Number 2, you've got particulate organic fouling that is literally gluing the beads together and throwing off their natural density. Number 3, the backwash just didn't run long enough. Or number 4, you've got an internal mechanical failure, like a broken distribution nozzle that's creating dead spots. Listen, if those resins don't separate, your hydrochloric acid and sodium hydroxide are going to neutralize the exact wrong beads, rendering the entire regeneration completely useless. The absolute crucial point here is understanding the physical state of your resin. Ideally, you want a perfectly sharp, clear interface where the lighter anion resin sits cleanly, right on top of the heavier cation resin. But in a failure state, you're looking at a muddy, blended mixed zone with a totally blurred interface. And the second you have that mixed zone, your chemistry breaks down entirely. All right, Section 4, Root Cause Investigation Steps. Let's do some forensics.
A rigorous, honest comparison of your expected plant parameters against the observed reality is the true hallmark of a veteran operator. You've got to pull out your system's design specs and compare them line by line with what's physically happening out there on the floor. Is your flow rate actually what the screen claims it is? Is that resin interface a distinct line, or is it a blurred mess?
Here's exactly how you run this forensic check. First, never ever blindly trust your control panel. You have to verify your flow meter accuracy against your actual pump curves. Second, get out of the control room, walk out to the vessel, grab a flashlight and look right through that sight glass so you can observe the fluidization dynamics with your own 2 eyes. Finally, if you suspect fouling, open up the manhole, drop a pipe in and take a core sample of the resin bed. You are hunting for physical fouling, broken beads, or those dreaded mud balls. Now for Section 5, Detailed Troubleshooting Action Plan, Executing the Cure.
You need a strict sequential approach to ensure the resin is physically prepped for chemicals without cross-contaminating. Step 1 is locking in your flow metrics. Step 2 is visually confirming that separation. And Step 3 is executing any pre-regeneration cleaning you might need, like an air scour or an extended backwash, before you even think about injecting your acid or caustic.
Let's talk numbers on that calibration. You must rigorously calibrate your backwash flow to hit exactly a 30 to 50% expansion of the resin bed. Why? Because that specific expansion range gives you the exact amount of hydraulic lift needed to separate the lighter anion beads from the denser cation beads without blasting them straight out of the top of the vessel.
Now, if your core sample showed that foulants have artificially bumped up the resin density by sticking everything together, a normal backwash just won't cut it. An extended backwash protocol is really the only way to break those clumps apart and get that natural buoyancy back. After the wash, you absolutely have to wait a few minutes for complete gravity settlement. Then, and only then, you check the sight glass to confirm that the lighter anion is resting entirely above the denser cation. Only after seeing that do you initiate your chemical draw.
Finally, Section 6, Summary and Key Takeaways. The prognosis.
I want you to remember these 4 pillars. First, achieving consistent resistivity over 15 megaohms strictly requires perfect physical resin separation. Second, visual confirmation through the sight glass is 100% mandatory. Screens can lie to you, but your eyes won't. Third, bed expansion has to be rigorously calibrated to that 30 to 50% mark. Never just guess it. And fourth, clean resins stratify properly, fouled resins will fail. If you can master the physical mechanics of the backwash cycle, you're going to eliminate the single biggest cause of chemical regeneration failure.
I'll leave you with this final thought. I really urge you to return to your facility and ask yourself this honestly. Is my system running on theoretical design assumptions, or am I operating based on observed physical reality? Go check your sight glasses, calibrate your flows, and never assume a mixed bed is just going to fix itself. Thanks for joining me for this explainer, and I'll catch you on the next deep dive.